If you pick up a rubber band and give it a tug, you can feel it fight back. You can watch it stretch out, and when you let go, it snaps right back to its original shape. Now, look at a steel guitar string. When you turn the metal tuning peg and pluck it, it feels completely solid. But that thick piece of steel is stretching exactly like the rubber band. We just can't easily see it with the naked eye. Absolute rigidity is an illusion. Every material in the physical world deforms when it is pushed or pulled. To understand how materials behave, engineers use two concepts. The first is stress. Stress is the invisible force you are applying to an object, the physical act of pushing or pulling on it. The second concept is strain. Strain is the measurable physical consequence of that force. It is the actual change in the object's shape or length. Stress is the cause, the effort you apply. Strain is the effect, the resulting deformation you can measure. How does a solid block of metal physically lengthen without breaking apart? It helps to zoom down to the microscopic level. You can visualize the inside of a solid material as a three-dimensional grid of atoms, interconnected by tiny, flexible springs. When you pull on a metal bar, you are pulling on that internal grid. You stretch millions of those microscopic springs all at once. This microscopic spring-like structure allows even the stiffest objects on Earth to flex and bend under a heavy load. Objects encounter forces in a few distinct ways. The first is tensile stress. This happens when forces pull the ends of a material apart, forcing those internal springs to stretch and lengthen the object. The opposite is compressive stress. This occurs when forces push inward from the outside, squishing the material together. You see this in the concrete pillars holding up the massive weight of a building. The pillar is being squeezed. Finally, we have shear stress. This happens when forces slide across each other in opposite directions, similar to how the two metal blades of a pair of scissors slide past each other to cut paper. Whether it's a supporting cable on a bridge or the pedal on your bicycle, structural loads break down into these three actions: pulling, pushing, or sliding. Let's go back to our rubber band. If you give it a gentle pull and let go, it returns to its original shape. This safe, bouncy region is the elastic zone. As long as the material stays in this zone, it will fully recover once the stress is removed. But think about a metal slinky. If you pull a slinky too far, the metal coils go completely straight. When you let go, they stay straight. You have crossed the threshold into the plastic zone. You've stretched the internal atomic springs past their physical capacity, resulting in permanent damage. Structural engineering focuses on keeping materials safely within their elastic limits, ensuring they never permanently deform or break under their everyday loads. Why do different materials react so differently to the same amount of force? Every substance on Earth has its own unique way of reacting to force, dictating exactly how much stress is required to produce a specific amount of strain. This chart shows how different materials behave when we apply force. The bottom measures the stretch, or strain, and the side measures the effort, or stress. For highly elastic materials like rubber, a tiny amount of stress creates a massive amount of strain. Stiff materials like steel produce a line that shoots almost straight up. It requires immense stress to create even a microscopic fraction of strain. These unique material limits help engineers decide whether a part needs to be made out of rubber, aluminum, or high-strength steel. Bright concluding tone. These invisible forces operate at a massive scale in the world around us. Towering skyscrapers are designed to experience strain. They sway and stretch against the heavy stress of high winds to avoid snapping. Human bones also rely on this principle. The bones in your legs endure compressive strain with every running footstep, acting as natural shock absorbers for your joints. A safe, resilient world relies on engineers knowing exactly how much a bridge or building can stretch, squish, and reliably bounce back without breaking.